people like Ophelia here and other theorists and our algorithm team at Quantum Motion really allows us to put that hardware development into perspective. As in, we can start to understand if we were to develop this particular architecture with such connectivity and such specifications, what are the results that we expect to have out of this? So that's one way, and of collaboration. So algorithms that are designed specifically for the hardware that is being developed. But I think there is another very important direction, which is that influenced by the theory side of things, the algorithm development side of the field, which is to influence hardware developers to try to push their limits, such as they modify so slightly their architecture within the realms of what is technologically possible, to get that extra bit of functionality that you would otherwise will not get to. No? So there needs to be to have a flow of information in the two directions and a strong and tight collaboration between the two realms of the field.
Yeah, I think those are all points I largely agree with. So just to sort of give the Quantinuum perspective, so the history of Quantinuum is that we were Cambridge Quantum, a software company based in Cambridge and a few other offices elsewhere, and Honeywell Quantum Solutions based in Colorado. And there was a merger. That was a business decision, but that was also a scientific decision. So we're now a full stack company. And I understand from my colleagues that that's been pretty well received, having kind of access all the way up, all the way down to qubits and layers, controlling qubits up to applications. For me, I kind of sit in the ivory tower at the top to a certain extent. And really, when I look at kind of the theorist's picture, I mean, something to bear in mind is I prove theorems in the unitary model of computation, basically, which, assuming closed quantum systems. And I prove these theorems for asymptotic results, so infinitely big systems. So neither of these two things are true, right? The system isn't closed, it's open, and we care about finite problem sizes. And as soon as you're in that regime, then there's practicality comes in, how much we try to avoid it as theorists. And really, one way to look at this is whether you talk about error qubits or physical qubits, those are statistical objects, not deterministic objects. And there's a saying that you tend to assume everything's Gaussian, and mathematicians think it's an empirically observed phenomenon, and experimentalists think it's a mathematical fact because it's a central limit theorem. But really, noise, the statistical character of the noise, has a huge impact on your actual guarantees from an application point of view. And it's really only by going and doing that measurement on the qubits, basically, and measuring, not just kind of coarse numbers like 2-qubit gate fidelity, but exactly how those errors manifest. And you actually understand that statistical character of that computation, you can actually kind of squeeze that extra bit out. So I'd say, it's certainly important to pay attention to the hardware as a theorist when it comes to practical application and when it comes to actually designing useful algorithms.
Thank you very much for that, Stephen. And kind of speaking about the kind of hardware, and I think Ophelia mentioned that some types of qubits have their limitations and some have their advantages. And every time I go on New Scientist or wherever, I look up quantum computing, big companies like IBM with their superconducting qubits, and they're the kind of key one here. But there's actually a lot more different types of qubits. For example, Fernando with silicon qubits. And I'm kind of wondering your opinions on that. Is it just going to be this one qubit that just dominates them all, one type of qubit, or are we kind of going to use each one maybe differently for different applications?
Yes, that's a very good question. Which technology is going to be the winning technology? No? And also the type of answer that you could give to that question is unclear. No? Is it going to be one or is it going to be several? I think it's very early days. No? And there is a very good phrase to describe where we are and what we could expect to to figure out at this moment from one of the fathers of this field, Scott Aronson, that said that basically you have all these qubits out there. Some are better than others in particular aspects. But to decide now which one is going to make the cut is like going to nursery. You have a look at the kids that are running around, and then you decide at that point who's going to be, say, a basketball star. It's very early days, no? So that's the message that we have there, no? From my perspective, no, and why I work on what I do, no, which is silicon qubits. I struggle to see a future in which any form of computation is not done on a silicon chip. all the computing that we have out there, either a laptop, a car, a phone, whatever, you name it, no? Sooner or later, it's made its transition to silicon technology. And that's what I believe in, that eventually we will be able to make robust and reliable quantum computers out of technology that looks very much like a transistors that you have in your phones or in your computers. So that's what wakes me up every day. That's what makes me do the research that I do with a lot of passion, because I would like to see a future in which we still maintain all our computing done on silicon technology. There is a but that is likely that that computer won't be on top of this table, won't be in your pocket, because necessarily the research that we do, the technology that we develop, it's done at ultra low temperatures. We are talking about 4 Kelvin and below, and typically millikelvin temperatures. So from my point of view, that computer, particularly if it's silicon or a solid state system, will very much be placed in a data center in a specialized location where you will have all the cooling technology and you will be accessing that computer remotely in the way that you do nowadays as well. When you do your complex calculations, you may already access data centers. So that may be the case in the future, that you will get your access to a quantum computer through the cloud, and that quantum computer will be at millikelvin temperatures or something like that.
Yeah, I can also comment. I agree with Fernando, because we work in the same, more or less same areas, like absolutely. Yeah, we have the same approach. Let me just try not to be so informal on silicon kind of qubits. In a sense that, there's a criteria that we like, the list of criteria that we have to make a good quantum computer and make a quantum computer. Okay, we call it the velocity features criteria. And you need to have a two-level system. You need to be able to initialize in one of the states. You need to be able to manipulate it. You need to have long coherence time, so you keep the stat level. If you want to manipulate, you still be able to manipulate for a long time. And then you need to repeat this many times, okay? And then you will have a quantum computer that's all. Now, silicon, I mean, yes, as Fernando said, I have it everywhere. Like 1 billion transistors, more than billions of transistors within one single chip. It's incredible how we can scale this. So silicon is a very attractive idea, but to be, quite frank, we don't know yet. So we don't know yet which is going to system that's going to win ultimately. Maybe there's other type of qubits that's going to come up and say, oh, there's this new type, and it's actually much better than anyone else that ever thought. Some years ago, there was this topologically protected qubits. If we ever can make a topological qubit, we out of the job in silicon qubits. We just go out. It turns out not to be so clear cut. So let's see how the field builds up. One thing I have to say is that I think if there is a qubit that's going to win, eventually I'll jump on that qubit. It's okay, it's fine. We all jump on the same qubit. It's fine, it's good. It's actually positive. If we ever decide which one is the winning qubit, we can all join forces on that qubit. But until now, we have to, try and see which one goes better. So for now, the superconductor qubits is winning. So they have like they have like hundreds of qubits now, so which is very impressive and quite cool actually. But let's see how it progresses. Yeah. Maybe difficult to scale it.
Yeah, so our public relations piece in price, I have to grab the microphone and flag for iron traps, otherwise I'll get to memory tomorrow. But yeah, so as I also mentioned computer science here, and for the past 5 years actually, I've set this exact question to my students as a discussion point, not because there's an objective answer, of course, but my view have changed a lot, and I think that's telling. So 5 years ago, I was of the view that superconducting was going to be the eminent technology because that's what everybody was doing, Google, IBM, etc. And because the surface code is particularly well mapped to what we believe we can do in terms of kind of the physical setup of those chips. And I used to say that iron trap's kind of the hipster choice there, sort of the also round. They've got a few interesting features and put them together in sort of different ways. And then there's a collection of other technologies. Whereas now it's a much flatter picture. So with iron traps, I think they're very interesting for near-term experiments. The high 2 qubit gate fidelities means they're very exciting to my experimentalist colleagues. There are, results suggesting topological pairs of iron trap qubits as well. It's not been explored, but that's a very exciting aspect as well. I think we need to still give a lot of respect to superconducting. That has been very heavily researched by a lot of very notable people who know what they're talking about. Silicon, I'm excited about as the big data aspect. Frankly, I want once this quantum computer, I want them to be stamped out fast and put in a kind of quantum computing data center. I think the existing technology around silicon is very exciting, and photonics is the genuine dark horse, and I'd be extremely keen to see a little bit more in terms of information in the public sphere. So it's a very nuanced picture. And one thing I think is quite telling is on the Cambridge quantum side of Quantinuum, we have stayed hardware agnostic because we don't want to, whilst we fully support and we're very excited about our hardware colleagues, we do recognise there's a heterogeneous picture that remain that way for some time.
Perhaps, just firstly to echo what Fernando said, it's very early. We're still seeing, all these different technologies do different things. As Stephen said, seeing the different kind of pros and cons there. And to provide another example of how it's changing quite rapidly and how your perceptions of technologies can kind of change over time. I don't think anyone's mentioned neutral atoms yet. Some colleagues, there was a quantum error correction conference in Australia a few weeks ago, and some colleagues were there, and there were some neutral atom results presented there that were very exciting. They haven't been in the literature yet, but it kind of showed that there'd been quite rapid developments in that particular technology. So just as another example of, we are still very early. Things are changing very rapidly. Getting better in different ways, and even kind of doing direct comparisons between technologies is quite difficult because there's no sort of single thing you can say you're aiming for right now.
Thank you all for that. Really like that.
So I think Riverlane is a good example. It seems like we are competing with different technologies, not necessarily. Most of the times we are actually learning from different techniques. So, a lot of technology that was for superconducting qubits, we are now using in the silicon-based computing. So, a lot of these problems we share. So, it's not always competing. We are learning.
Yeah. So I suppose now I'm going to open it up to everyone to see if anyone here has any questions. And for the best question, we can wait. I suppose the panelists can judge who's best question. But you can win my coloring book on coloring adventures of Cube with the Cat Guys. So you better ask some good questions. So if anyone has some questions, please raise your hand. Yeah.
So, if you started off talking about how you need engineers and researchers to work so actually was yeah. And Steve, you also spoke about how when you solve problems, you abstract them away. And I guess one of the things that is very different in quantum computing to classical sort of algorithms development is how high the bar of entry is, both for working in theory as well as working in experiment. I mean, there's not much you can do without at least a bachelor's degree. Whereas if we look at what's happening in I don't know, like artificial intelligence, for instance, like people can basically self-teach themselves the necessary theory and then make contributions or like explore novel applications of the technology. And my question is, do you think that as quantum computing becomes more mainstream, this is going to change and this bar of entry is going to become lower, or is it always going to be sort of a field that you need lots of technical training to enter?
That's a great question. You very nicely compared with people working on artificial intelligence domain. There's a large community there that's organized itself very well. Particularly, it's provided free material for people to learn and to upskill themselves in their own time, whether they are studying or doing something else. You can get some key aspects of machine learning, artificial intelligence. The quantum computing community maybe is not yet that big, but we are starting to see that there's a necessity to do something very similar to that, which is to provide education to people in the form of face-to-face courses or even MOOCs, massive online open courses, to train themselves in their own time. No? The reason why this has not happened much, I think, is maybe boils down to the size of the field. We are not that many just yet, but since we are growing, it's trying to see much more of this. Nowadays, you can find online courses that will teach you specific aspects of quantum computing. You can take them as you study and prepare yourself, no, for entering the business. And there will be more of this. No? Actually, in Quantum Motion, we are preparing our own program for upskilling people from day one. Particularly, this is targeted to bachelor or master students, because we foresee that there is not anymore a necessity to have a PhD in quantum physics to get into this. It's not anymore the field of just a bunch of physicists. This is a global endeavor that requires engineers, electrical engineers, mechanical engineers, computer scientists, chemists, you name it. No? It's much more global. So that's going to happen, and eventually happens. As I said, I think nowadays the industry as well is much more welcoming to bringing people that may not have all the training, but the industry is ready to give you that training and upskill you such that you can start producing and be a very useful and contributing member to this field.
Anyone else have a question? Yeah.
Yeah, two questions, if that's okay. So the first one is, as kind of industry scientists, how do you exactly reconcile the gap between, say, the objective of quantum theorists and, on the other hand, kind of the commerciality and business needs of developing a product? Because I'd imagine there's sort of difference in level that you just have to stop the science, roll on the product. I guess related to that is, what are some strategies that you have out to make this? that's not. I was wondering, how would you highlight how much development in terms of overcoming the limitations of this earlier model has?
Perhaps on the first question, so just to check I understand, you're asking about kind of sort of as individual scientists reconciling kind of the desire to do scientific research with the fact that we're in a company and that has. So I would say for me personally, that's actually like kind of the ideal combination. I sort of like that kind of research that has direction and is driven towards wanting to get to kind of useful end applications. It obviously means you don't have total freedom, but I think that kind of balance actually for me is a big positive thing. I would say.
Yeah, on the second part of the first question, I mean, the answer is you don't look for layman investors, you need informed investors who are going to go with you the steps away and have realistic expectations from the start of the way. I didn't actually catch the second question. It's to do with cryptography.
Like QKD encryption. So I've done some theoretical research into the BPA24 model and like into these benefits on like various limitation factor, just all that noises, Trojan noise attack, whatever. Like how far do you think this technology has come like today that probably like overcame some of the early limitations? And whether it's like will be commercial in the next 5 to 10 years.
I'm not familiar with that more. So already know what Steve, you want to say about this?
Yeah, I'm not super familiar, but I mean I'm familiar with the theory, with the experimental practice. There are results on QKD. Noise is, I mean it's simpler to take into account noise in kind of information protocols than computational protocols. You can kind of do something which is more closely analogous to what you do classically, but it is still the corruptive effect, which still needs your kind of quantum protection. But yeah, I think it's just a case of driving noise down, driving the corruption up. Really, there are results in Shiba, in Cambridge, where we've got nice kind of benchmark results, but we're still at that stage of benchmark results, and yeah, proving long distances pure and that kind of thing. But I think, yeah, I don't know if anybody else wants to add. I think that's perhaps all I'm probably already spoken on. I'm qualified to say that.
Thank you, Steve, for that. Is there any other questions? Older?
I think my question is kind of related to the previous one. It's like, are other computers going to be like the security threat? And what do I mean by security threat is more like not just in the context of cryptography, but like because you all are pushing the boundaries right now, that maybe there are some applications that you never thought of. And how do you, as scientists and also as commercial people, reconcile that fact that your product might not be when you are producing a product, it might not be used as you intended it to be. It's not like a philosophical question. I'm not sure how much I'm deviating right now.
So you refer more to the ethics of quantum computing and
You can be whatever you want.
and the honesty of the scientists and the people using it. I mean, I think it's like with any other technology. Technology can be used for good, can be used for bad. There are two sides of the coin. No? It's probably fair to say that everyone that's sitting here in quantum computing are doing it for the will to deliver a useful technology. And by useful, we mean that serves to improve our lives. No? I don't know. It's difficult to say whether an application will be developed in the future that doesn't serve that primary role of a scientist. It could well be, no? I mean, we've seen in history there's been different ways in which technology development has gone, but I don't know. I think the community that we work in, it's very research oriented with the mentality to deliver something, even though it becomes eventually a commercial product that can be useful and helpful.
I think just to follow up a little bit, the reason why I'm asking this question is because like a very like examples like Ophelia, like right now people are figuring in internally like the ethics versus like commercial. So I'm not sure about your view on that. I feel like it's a very good framework, especially in both industries that are growing quite rapidly.
Yeah, I mean, I think this is an unanswerable question, really. I mean, if you push technology out into the world, then it will be used in whatever way people use it, and you can ask any inventor back through time, you know, the end result of what they do. But one thing our founder Ilyas from Quantum Science has been very active in is trying to build ethics into the quantum sector from the start, and trying to build community possibility support becomes an ethical approach to start. That will only go so far. That's kind of this closed shop mentality we have to a certain extent at the moment, which we want to break down and become more open, but with it comes a risk that people can use the technology as they see fit. And those two things go together really.
And then is the final question, does anyone have that?
Hi, so I just want to ask about some analogies between classical computers and quantum computers. So like for myself, I first learned about this area because I was interested in classical computer sciences. And for now, what I have learned is that there are still some basic differences, but in the aspect of hardware, like you mentioned that we're trying to build something like the transistors in the classical computers, and also from the software, from the algorithms aspects. What I have learned for now is that we have Python packages to manipulate the qubits, and most algorithms we have used is written in the languages that we're using for classical computers. So I was just wondering if are we trying to build the quantum computer so that it's more like the classical computers that we're using right now, or would it like open up brand new fields in computer sciences, like new hardwares, of course new hardwares, and like new programming languages and that sort of thing?
So that I guess the answer is it's very different. It's really very different. So we use the analogy for computers because it's what we have, but the way it works and the way the conception and the algorithms, it's a totally new different world. So even the problems that we can solve with a quantum computer are not the same type of problems, and that's the reason we say that a quantum computer is not going to replace a classical computer. So a quantum computer is much more like a calculator, a very good calculator. It can be used. So one of the big applications, like in principle, it can simulate the world. And the idea behind that the quantum computer already uses the principles of quantum mechanics to make a calculation. That's the fact it already has encoded, So this is already one of the basic ideas. You want to solve a equation, Schrodinger equation. You can write a Hamiltonian and you can try to solve that, and then you can even try to put a classical computer to solve. The problem is that it's an extremely inefficient way of solving a problem. And then we understood from the very beginning of using quantum computer, we understood that problem was already very hard to solve with a classical computer. So we invented this new concept of saying, okay, let's use a computer that already has some things in code, like some quantum physics already there, to use it to solve these problems. but then you have to redo everything. You have to redo the hardware itself, but you also have to redo the algorithm. So it's only the namespace that more or less the same. So we are opening a completely new field. It's a complete new field. There's nothing. I mean, you can do analogies, but that's what's fascinating. It's what we do. So everything is.
Yeah, perhaps just sort of repeating things people have already said. So when we're thinking about quantum computers, you know, in some length of time from now, when they are large and capable of doing useful calculations, these will, as everyone has said, be only useful for these specific types of calculations which quantum computers are useful. And as was also said, these aren't going to be things that will be sitting around in every room, every computer room in a college or something. It will be sort of select users, perhaps accessing large data centers for the specific problem they want to solve. Exactly what that access will look like in terms of any analogy to kind of existing interfaces to supercomputers or software, I think it's another thing. It's too early to say. In general, at the moment, when we think about access to a quantum computer, we're sort of several levels below those eventual end users. It kind of has to be a kind of a lower level. So yeah, exactly how software and things will look at the very end when we get there, I think it's simple to say.
Okay, you want to go say something, Stephen?
Yeah, did you say this is the last?
Yeah.
Yeah, so I was just going to finish with a major controversy and contradict. So you know, one way to look at quantum computer is it's nothing but a machine multiplying together very, very large matrices. And so if you can think back to your classical workflow, so you've got something which is just a big matrix operation and it's a quantum computer. It's a little bit more thinking than that, but there is a way of thinking about quantum computation within classical workflows, and these two. You know, these 2 points of view are both complementary, both valid actually, but seeing actually computing competition.
Thank you very much for all your time, guys, and being here with us today. And thank you everyone for coming as well and hearing everyone speak in your questions. I personally think the first question is amazing, so I would say you would look to the first question. And yeah, thank you all again. Thank you. Enjoy.
Second.